Let's now solve a couple of exam questions regarding the circle. There's one thing you should know about questions about the circle, and that is that very often they link this to something that you learn in the chapter about quadratics, which is the one tool called the discriminant. I urge you, particularly for the second question that we are going to cover, uh, that you go and watch those lessons and see exercises about the discriminant so you can understand more thoroughly what I'm going to explain, particularly on question 2. But the thing is that every time you solve exam questions about the circle, chances are that you'll have to use the idea of discriminant. Let's look at this first question. Again, you look at this, and some of you may just, by the simple fact that the schematics look complicated, start telling yourselves that you are not going to be able to solve this just because of the looks of it. Let's read and let's see that this is actually broken down into simple questions. We have a diagram that shows a circle P, the big one, that has center 0, 2, and radius 10, and a tangent to the circle at the point A with coordinates 6, 10. So you have the coordinates of that point. It also shows a second circle Q with center at the point where this tangent meets the x-axis, the y-axis. So this is the center of Q. And you also know the radius of this one, which is 5 square root of 5 over 2. You are first being asked just to write down the equation of circle P. All right? And you have all the information here. You have the center and you have the radius. So what do? You just plug in these values into the equation. So it's x minus 0, or just x squared, plus y minus 2 squared equals the radius square, or 100. It's done. All right? That's why it is only one point. Find the equation of the tangent to the circle P at A. The equation of the tangent to the circle P at A. This is a straight line. What do you need to know the gradient? What do you need to know the equation of a straight line? You need the straight line's gradient and the y-intercept. Let's start with the gradient. How will you get the gradient of this line? You know the coordinates of the center of the circle. You know the coordinates of point A, so you can get the gradient of this line over here. The equation of that one is going to be perpendicular. The gradient of that one is going to be perpendicular. You can get it very easily. And the y-intercept is just the y-coordinate of the center of the circle Q. So first of all, I got the gradient of line CA because I have the coordinates of both. And the gradient of that one is 4/3, which means that the gradient of the line that I want is minus 3 over 4. Using the equation, the coordinates of point A, I can get the full equation of that line. First, I get the y-intercept. So this is going to be the equation of the tangent, minus 3x over 4 plus 29 over 2. I actually put it in a simpler way, and I prefer writing it like this. And you're going to see later on why I just put it like that. Then we had the linear C. Find the equation of circle Q, and hence verify that the y-coordinates of both of the points of intersection of the two circles are 11. So you need to get the equation of this circle and prove that the y-intercept of these two, the y-coordinate of these 2 points of intersection of this circle with that one, they both have value 11. All right, so first of all, the equation of that circle. What you need to get the equation of a circle, you need the coordinates of the center, which you already have. You know that this is the y-intercept of this line, so the x-coordinate is 0 and the y-coordinate is 19, like you can see here from the equation. Where is it? Okay, here. The y coordinate is 29 over 2. So the equation of q is going to be given according to these coordinates of the center. So it's x minus 0 squared plus y minus 29 over 2 squared equals, the radius was given. It was over here. The radius was this. So if you square this, this is what you get, 125 over 4. So here you have already the equation. You also need to prove that the points of intersection of the two circles have y coordinate 11. So in order for you to get points of intersection, if you have straight lines, I just advise you to equal one to the other. If you have curves, I advise you to use simultaneous equations. So you have to put here the equation of one of the circles and here the equation of the other circle and try to figure out the values for which they are the same. In this case, I just used elimination. I eliminated x squared, and this is what I get. This minus this. I just expand this. And eventually doing all the algebraic manipulation and putting together like terms, eventually I will get this equation, which leads to the value y equals 11 as asked to begin with. Then last question was, find the coordinates of the points of intersection of the tangent and circle Q, giving the answers. Insert form. Again, the points of intersection, the coordinates of the points of intersection of the tangent and circle Q. Of the tangent and circle Q. So here and here. Again, points of intersection. What you have to do, you have to use simultaneous equations. Here you have the equation of a straight line. Here you have the equation of a circle Q. And now solve it. I used substitution. So on this equation of the circle Q, I just put the information about y. So here, this y is going to be this stuff. I'll have to simplify first what I have inside the brackets and then expand. And eventually, this is what I get. Don't forget that 29 halves minus 29 halves, this eliminates. So this is just going to be this, which is basically 25x squared equals 500, x squared equals 20, and x equals plus and minus 2 square root of 5. Then I have to substitute this value on the equation where I left it, the top equation, and this is what I get eventually. The x is plus or minus 2 square root of 5, and the y is 29 plus or minus 3 square root of 5. Don't forget that you had to give your last answer as surds. So this is what you present. And that will be it for this question. The next one is the one that requires the idea of the discriminant, and I'll let you know where it is going to be needed. You don't have any drawing, you just have the information that the equation of a circle is x minus a squared plus y minus 3 squared equals 20. This is a circle, and then you have a straight line with equation fully provided. That is a tangent to the circle at point P. Show that one possible value of a is 4 and find the other possible value. A is going to be the x coordinate of the center. All right? You know the y coordinate, so you know exactly where the circle is going to move, all possible positions. You also know the radius of the circle. You just don't know where the x coordinate is, where to fix it, right? You also know the equation of a straight line is 1/2 of x plus 6. So you have to stick the circle in a position where this line is going to be tangent to it, all right? This is the visual idea that you need to have in order to solve the question. So here you have the information being provided. And if you know that this line is a tangent to the circle, you know that the line is going to touch the circle only once, right? It is a tangent, so it touches the circle only once. Here it doesn't touch. Imagine here a circle. Here it doesn't touch any in any point. When the circle gets closer or the line that gets closer, here is going to touch once. Here it would go to touch twice until it passes the circle, and then once again and zero. Know what I mean? You want the line to touch the circle only once because it is a tangent. So what do? You may just plug in the value of y over here. You know that the line has equation y equals 1/2 of x plus 6. So if you just put this over here as y on the equation of the circle, you can solve it for x. That's what I did. Here, instead of y, I just write that down. I expand both. And eventually, I get this equation. Don't forget what this is. A is a number, right? So this is going to be the coefficient of x, and this is going to be a number as a function of a. And 5/4 is the coefficient of x squared. So this is what? This is a parabola, all right? A parabola with general equation ax squared plus bx plus c, in which this is your a, this is your b, and this is your c, right? And this is where the idea of discriminant enters. As we're going to see later on the chapter about quadratics, the next chapter, if you have a situation in which you want to get the points of intersection and this point is only one, you can use one thing called a discriminant, and later on I'll explain what the discriminant is, which is given by this formula over here, b squared minus 4ac. You may remember this as what you have inside the square root on the quadratic formula, and the reason is because this is actually what it is. All right, so b squared minus 4ac, in which a, b, and c are the coefficients of the quadratic formula, ax squared plus bx plus c. All right, so the discriminant, if you want something to a line to touch a circle, in this case only once, you have to equal it to 0. Again, I'll explain why later. For now, you just need to know that. And by the time you do an exam anyway, you know all chapters, so you can use that tool on this particular topic. So you just have to substitute b, a, and c. What is b? B is the coefficient of x, which in this case is 3 minus 2a. A is the coefficient of x squared. And c is the value of the number with no x. So that's what I did over here. B squared minus 4ac. Expand the whole thing, and now you have an equation in terms of a. So you just have to combine like terms. Eventually, you get into this, which can be factorized into that, which gives you the answers that you need. A equals 16 or a equals 4 as required. One of them is 4 and the other one is minus 16. Next. For a equals 4, now let's assume that a is 4 and not minus 16. Find the equation of the normal to the circle at P. The normal to the circle at P. Now we know what the value of a is 4. So we can plug it in here in the formula, and we already have the full equation of the circle. All right? And having this, you already have the coordinates of the center. So it's going to be 4, 3. The normal is going to have the gradient minus 2. Why? The gradient of the tangent was 1/2, so the gradient of the normal to the tangent is minus 1 over that, so minus 2. Since it is a normal to a tangent, you should know that a normal to any tangent of a circle passes through its center, obviously. It's radial. And if it is radial, you know the coordinate of one of the points of the line, which is the center, 4, 3. So once you know that, you can plug it in the equation of a straight line to get the value of the y-intercept, which is 11. So here you have the equation that you were being asked, the equation of the line of the normal to the circle at P. For A equals 4, again, this is for the next sub-question. Find the equations of the two tangents to the circle which are parallel to the normal found in B. Now you found the equation of a normal, and you want the equations now of the two tangents that are that are parallel to the normal. So if you imagine here a circle, and this is a normal, you want the equation of the two tangents, this one over here and this one over here. All right, this and this, that are parallel to this. So if they are parallel, you should know that the gradient of these lines are going to be the same as the normals. And what was the gradient of the normal? It was minus 2. So the tangents have the same gradient as the normal. So they'll have equations y equals minus 2x plus c. What is going to be different on these two lines is the value of the y-intercept, not the gradient. The gradient is the same and equals minus 2. We already know that. So let's calculate the points of intersection of the circle with these lines to get the values of C. What is going to define the position of these two lines for which we already know the gradients? Is the point where they touch the circle only once. So again, we want to get equations of lines of that are tangent to curves. So again, we have to use the discriminant. B squared minus 4ac. And let me see one thing. Yeah, not yet. We're going to use the discriminant a little further on. First of all, we have to, like before, plug in this this equation over here on the equation of the circle, right? That's what I did over here. So the equation of the circle was x minus 4, y minus 3, and y is what? Minus 3 squared. So what was y? It was minus 2x plus c. So I put it over here. Minus 3 squared equals 20. Okay? This is what you have. I just substituted this y by this. Expand. Put together terms that are like terms, and this is what I get. Again, this is the equation of a parabola in terms of c. This is the value of a, ax squared, a is 5. This is the value of b, the coefficient of x, 4 minus 4c, and this is the value of c, as the last term of the equation of a parabola, ax squared plus bx plus c. All right? You have now two c's. Do not confuse those. All right? As I was saying, here is the part where the discriminant takes place. If we want tangents, there must only be one value of x that satisfies this equation, which means again that the discriminant has to be equal to 0. And then again, if this is the first time you are hearing about the discriminant, don't worry, because this is going to be part of chapter 2. If you are watching this video after you learn what discriminant is, this is going to make much more sense. So the discriminant has to equal to 0. So you just substitute on the formula for the discriminant the values of b, a, and c. B is this. So you have 4 minus 4c squared minus 4 times a, 5, times c, which is all that stuff. So expand the brackets, combine like terms. Here I divided the whole thing by -4 to make it a simpler quadratic. I can see that this can be factorized into this. So I'll get the two values of C as being 1 and 21. So the equations that you want, the equations of the two tangents, one is for the moment where C is 1, so it's going to be minus 2x plus 1. And the other one is when C is 21, so y equals minus 2x plus 21. So by solving this equation and using the discriminant, you were able to find the values that will define the two tangents that you wanted, for which you already knew the gradient. The last thing remaining to define the lines were the value of the y-intercept. And this is how you get them. The two values of the y-intercept, the two equations that you want.